Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the last two classes, I talked about some of the problems from all the different sections which I covered in this class. So I already covered the problems from the carbocation and then also from the carbene nitrene. In the today's class, I am going to focus some of the problem from carbon ion and also from the Grignard and organolithium. So those are also can be considered as like some sort of a carbon ion, correct? So let's talk about the problems. So the first problem is again I think these are the problems came all the different competitive exams. So here what we are seeing here, we can see there is a amide linkage here, and you are treating with sec-butyl lithium with a timeda, and then there is electrophile methyl iodide. So if you remember, I think I talked about directed lithiation, correct? And at that time I also talked about that if you have some sort of a directing group which attached with the aromatic ring, if you can say directing group, then that can what that can do. Now if the directing group has some sort of a group which can coordinate with your, which can be a Lewis basic character, so that which can coordinate with your lithium, then when you have the RLI, which could be sec-butyl lithium, dibutyl lithium, so that can allow the lithiation to be happen to the next proton. So this R is actually R minus, correct? So you can think about this as a minus and this as a plus. So this can able to take this proton and generate a corresponding carbon ion. And also I talk about there are several different directing groups, correct? So this is one of the example of similar problems. And now if you treat with the electrophile, then you will be able to introduce a electrophile there. So in this problem, what is happening? You have a carbonyl with this, with a so here you can think about this. This can chelate with your lithium and the corresponding sec-butyl lithium. This can able to take this proton, generate a carbon ion. And now if you treat with methyl iodide, what is going to happen? So it is get rid of the iodine, correct? So that can act as an electrophile to introduce a methyl group. So this is acting as a directing group to introduce methyl in the ortho position of this amide. So now if you look into all the different answer, we can find only the answer B which has the correct structure, correct, which is showing the introduction of methyl group in this position. So you can see that is the correct answer for this problem. So let's move into the next problem. Again this is from the Grignard chemistry. So I already talked about lot about the Grignard chemistry. And one of the important thing, if you remember, I talk about different type of Grignard chemistry, primary, secondary, tertiary. And one thing I mentioned that Professor Nochel's group developed one important chemistry, that if you want to go for a magnesium. So we have learned about that organolithium can be, I think you have already previously seen that if you have this corresponding bromide, then if you use a N-butyl lithium through metal halogen exchange, we already talk about this. We spend a lot of time talking about this type of reaction. Okay, so this is a so using organolithium, you are doing a metal halogen exchange. Okay, but this can be also done using Grignard reagent. Okay, so this discovery so this is a very important discovery, because a lot of the reaction, if you have N-butyl lithium, they are very reactive, but the Grignard was not that reactive compared to the lithium. So you can able to tolerate a lot of different functional groups. I think I mentioned during that time that if you want to use some sort of a functional group like cyanide or ester or carbonyl. So now we are talking about this type of substrate. So here if you treat with N-butyl lithium, what is going to happen? It will go for metal halogen exchange, but it will attack to the cyanide also. So that's why the idea is if you use some sort of a Hinder-Grignard reagent, like something like isopropyl magnesium bromide, then it can go for the Grignard reagent can also go for a metal halogen exchange, and it can allow you to generate the corresponding, and these reactions happens at some sort of low temperature, less than some -10 -20 degrees. Around that temperature this reaction happen. It can allow you to generate corresponding Grignard reagent here, and keeping this cyanide and other functional group intact. Okay. And now once you treat with the corresponding electrophile, this is allyl bromide, then this Grignard can go into attack here to get rid of the corresponding bromide, and you will be able to introduce the corresponding. So again, I think one of the advantage of using this Grignard method over the organolithium is that this metal halogen exchange happening at the low temperature, where it is not attacking the corresponding cyanide, so that is remaining intact, and you are able to generate the corresponding Grignard, and you can do the some sort of a reaction with the corresponding electrophile, some sort of a SN2 type reaction with the electrophile to get to the corresponding product. So now if you look into all the different answer, we can see this this cannot be the right answer, the bromine is there, neither this one. So this one looks the correct answer, where the bromine was replaced with the allyl group. Okay, so this is the correct option here. So moving further in this problem, what we are seeing here, let's first look into. So we can see clearly there is a dye in here, and then you have some sort of OCOCH2CH3. Okay, so it's not acetate, you have a ethyl group here. Now if you treat with LDA, so if you remember I talk about LDA, and I talk this is a strong base used for several deprotonation reaction. There is two isopropyl group, and then it's the N lithium. So this can able to if you see in this particular compound, this is the proton which is acidic. So LD can able to go for the deprotonation, and it is going to generate, and then what you are treating with after the LDA, that means once you generate the lithium, you are treating with TBDMS chloride. So that can take you all the way to the corresponding. So let me just wipe this part which you don't need here, you already. So what is going to happen here, we end up forming OTBDMS. Okay. And now what we are doing after the first step, we are treating this with this compound. So you can see there is a good, so this diene is electron rich, and you have a dienophile. So which reaction you have learned? So there is a 4 pi 2 pi, so this is a 4 plus 2 cycloaddition. So you are giving this dienophile and heat, so that can take you to the 4 plus 2. Now the question comes is these are not symmetrical, neither the diene or the dienophile. So there is a possibility of different type of regioisomer. So question comes now, once this the disulfide is happening, which side of the diene is more electron rich, and which side of dienophile is electron deficient? Those two parts going to combine. So now if you look into the electron density wise, this oxygen can give the lone pair electron density here, and this can give more electron density onto this particular carbon. As well as once you have a electron withdrawing group, this is the carbon will be electron deficient. That means this is the two part going to be combined. Okay, you can able to find out from the coefficient of this particular carbon. From there also you can see that this will be the highest coefficient here. This will be the lowest coefficient in terms of the electron withdrawing group. So they are going to get combined, and then that can able to form the . Again, one of the other thing is once the Diels-Alder reaction happening, they are approaching in the same phase, so you end up getting to the this particular diastereomer. Okay. So after formation of this, what we are doing, we are treating this also, so again I think if you look into this particular compound, now you can see that there is a 1, 2, 3, and again 1, 2, 3. Now if I can draw them properly, okay, we can clearly see a possibility of a 3,3 sigmatopic rearrangement. So under heat, the 3,3 sigmatopic shift is going to occur. That is, cleavage of this carbon oxygen bond, formation of carbon oxygen double bond. We already talk about, and then one of the important thing, if you see this 3,3 sigmatopic rearrangement is happening where this new bond formation is also happening from the same phase where the oxygen bond was there. So that means you end up so you will have you end up as C double O OTBDMS, and you will have a methyl here. Okay, and then there is a ester here. So now what is going to happen, if you look into all the different options, you don't find these options, and again then they put water, and of course in this reaction this can there is a possibility that this OTBDMS is going to get deprotected, and if it is getting deprotected, then what is going to happen, this can convert to the corresponding acid. So now if you look into all these different examples, these are in the 1, 2, 3 position, in the 1, 4 position. So if you look into all the answer, this is the only answer where you can see these are in the 2, 3, 4. Of course, one thing going to happen, there is a new bond going to form between these, which we missed here. I think you can see here when the Claisen arrangement is happening, there is a new bond formation happening between 1 and 2. Okay. So this is going to be the correct product here. Okay. So there is couple of things happening. First, you can see deprotonations, then there is a 4+2, and then there is a Claisen rearrangement. Again, you can see this is the correct options here. So moving further, this is a very interesting problem here. We can see there is a 5,5 fused ring with where the 2 hydrogens in the cis is first treating with LDA minus 50 Celsius with then giving phenyl selenium chloride, and then again LDA minus 50 Celsius with methyl iodide. So what will be the structure A, and then if you do the H2O2 and 50 Celsius, what will be the structure B. Okay. So let's start about first thing, what will be the structure of A. Again, to understand this, I think I am going to use this model to describe these things very nicely. So first thing is that in this reaction, first step is happening a deprotonation. Once you use this LDA, this is going to after this proton to generate a carbon ion. So this can generate a carbon ion, and then this will make a corresponding enolate. Now if you try to look into the model, So let's look into the model for a second to understand how this reaction, which phase the electrophile going to approach. Okay, so can we focus on the model? So we are trying to understand in this particular cases, you can see these are the two hydrogens, correct? They are in the above phase, and I am talking about you already form a double bond here between these two carbon, correct? Because you form the enolate. Now the question comes that when the when you are going to trap a electrophile, the electrophile can come from this phase, the top phase, or it can come from the bottom phase. Okay. Now you can clearly see that if you are coming from the bottom phase, what are the interaction it has to have? These are the carbon-carbon bonds of the other cyclopentane ring. These are actually going to be put a steric interactions with the upcoming nucleophile, correct? Because these are, see, if you look into the model, you can see there is some sort of a cavity here in the bottom side. So once something is approaching through the cavity, it is actually getting interacted with this particular another cyclopentane ring. You can see here. So these are actually, that's why the nucleophile, when it is approaching here in this direction, electrophile when it is coming in this side, it is getting a steric hindrance. But if it is coming on the top side of it, then there is only these two hydrogen which is getting interaction. Otherwise, you can see this is the double bond. There is no other interaction. It is actually, so that's why the electrophile will prefer to come from this top phase. Okay, so that is the most preferable approach. Okay, so let's go back to the problem again. So if that is the case, what is going to happen here? After the enolate formation, so it is going to form, so it is going to trap the selenium pH. Okay, so it is first from the enolate and then it is going to trap. So this will be your first thing. Then what is going to happen? You give again LDA. If you give LDA again, then the proton here, this is going to be abstracted, generate a carbon ion here, and you again able to make another enolate. Okay. And you have this selenium pH. Now again, once you treat with another electrophile, what is going to happen? You treat with methyl iodide. Again, the approach of the methyl will be from the top phase. Again, it don't want to get the steric interaction when it comes from through the cavity, so it will better to approach from the top phase. So in that case, what is going to happen? You end up generating this particular product. So again, your methyl will be up and selenium will be down. So this will be your compound A. Okay. Now what is going to happen if you treat with H2O2? Once you take this compound and treat with H2O2, so let's draw the structure which is going to be the compound A. So it is going to convert. So you have at the beginning ACPH, H2 going to oxidize it. Okay, it's going to oxidize the corresponding selenium because this part will be remain unreacted. But what is going to happen here? You have a selenium oxide. And now once you have a selenium oxide, what is going to happen? Now you can think about this type of reaction here, where If you remember that if you have a methyl group here, and think about these 3 proton and then the selenium oxide, you can think about as a O minus, selenium plus, this will be able to take this proton, form a double bond, and this is participating, this will eliminate. Okay. So there will be syn elimination going to happen, which will end up generating this exocyclic olefin. Okay. So what is going to happen at the end? You got, this is your A. So let's look for what is the A compound going to look like. I think we can see here also look like our product. In option C also has the product. But now if you compare that the option B, then we can only see in this particular problem we are having this exocyclic olefin. So that means the option A is the correct option here. Okay. Let's move into the next problem. So here again what we are seeing a pyridine, and then we are seeing a mom protection of this corresponding 3 hydroxy group. You are treating with terbutyl lithium, and then you are treating with ICH2CH2Cl. Okay. So here what is going to happen if you have that. Okay. Again now we can understand that once you have a terbutyl lithium and once you have a pyridine, what is going to happen? The terbutyl lithium can abstract a proton from the pyridine and generate some sort of a carbon ion. Now we have to understand that there is a, again if you have I think in the previous classes when I was talking about the pyridine, one thing I have clearly mentioned that once you talk about the abstraction of this 3 different proton and the rate of abstraction, if this is 1, this is 72, this is 700. Okay. So formation of carbon ion in case of pyridine, in the 4 position is the most preferred one. So here also instead of the 2 position, that means in these cases you will see that the mom protecting group can able to act as a directing group here. So that the terbutyl minus can able to take this proton, generate a corresponding carbon ion, okay, and then once you treat with this corresponding ICH2CH2Cl, it will be taking the corresponding iodine and going to convert to it can iodinate in this position. Okay. So now if you look into all the different products, that is not the product, and the only cases when you come to the C, you can see this is the correct structure because you have formed the carbon ion at the C4 position and you got the iodine into it. Yeah, the option C is the correct option here. Again, this is another very similar question of the directed lithiation. So we have learned directed lithiation at the beginning. You can see in case of benzene ring, you will not able to find a difference, but once you come to the pyridine, then the C4 carbon ion is more stable than the C2. Again, this is a unsymmetrical scenario here. We are talking about directed lithiation. Again, there are several problems come from directed lithiation in the competitive exams. So that's why I brought several different questions. This is again another mom protection, and you have the CH3 group here. So let's try to understand. Again, you are using a sec-butyl lithium and CO2 as electrophile, and you are treating with the H3O plus to protonate. So if you try to write from this structure, we can clearly understand there is 2 different possibilities, correct? One is it can bind with the lithium, sorry for that, and if you see this is R, then this can able to take this proton to generate a carbon ion. So there is a possibility number 1. Or there is another possibility here. So now, in these two possibilities, which carbon will be forming? Because once you can decide that, you can get the answer, right? Now, if you look into these two different tangent states where it is forming, you can clearly understand that in this particular case, if you give them B and this is A, in case of B, what is happening? Because of the presence of this methyl group, there is a steric interaction. There is when it is going to, because it has to go through a chelation model. So the chelation with the oxygen is very important for this direct lithiation. Now, if there is a group like CH3, which is not really, if you instead of CH3, if you have a OCH3, then that can also take part in the chelation. But CH3 group cannot take part in the chelation, so it kind of acts as a kind of steric, so it actually have a steric interaction that will not allow you to form, this has a major one, you will get the other one where it is forming in this position is the major one. And if this is the major one, then from there if you treat with CO2, what is going to happen? You end up introducing CO2 minus, correct, and you have a CH3 here, and now once you give H3O plus, you will able to get to the corresponding product. Okay. Now, if you look into all the different options, we can clearly see option A is not possible, option B is not possible. Only in case of option C, we can see that is the correct structure of us. So, the option C is the correct answer. Again, there is another important problem always comes in the exam, where I think this is an example of, you take a carbonyl compound, you take tosyl hydrogen and ethanol, and then you treat with excess butyl lithium, and finally use DMF. So there could be several different variation in this type of questions, but if you see the first two reagent can directing you what you are going to form. Now the last one could be DMF, could be other different electrophile, based on that you will get a different product. So let's try to understand. So this is an example of a Shapiro reaction. I think I already talked about Shapiro reaction when I talk about organolithium chemistry. If you forgot, please go back to that notes. Okay. So let's try to understand what you are going to get in this particular reaction. So which will be your product. So let's try to draw the mechanism of this reaction. So what you have learned, that if you have a hydrazine and you have a carbonyl compound, the first thing is formation of hydrazone. So once you have tosyl NH2, the tosyl hydrazine going to form so there will be loss of water. You are using ethanol as a solvent in this reaction. I am sure nobody has any doubt up to this. Okay. And then now what you are doing, we are treating N-butyl lithium excess. So once you have N-butyl lithium, the first thing is you can see in this molecule, this is the NH proton is the acidic one. So there will be deprotonation of that. N minus TS. If you have a more n-metal lithium, so next this will be the acidic proton. So this will be taken by n-metal lithium to generate the corresponding carbon ion. This will come back. This will form a nitrogen-nitrogen double bond, get rid of the tosyl. The nitrogen minus and double bond here. This minus will come back and cleave this carbon nitrogen bond. Okay, so you have already a lithium plus in the medium, so you can write as a carbon ion or you can write as a vinyl lithium. Either way is fine. But once you have this corresponding lithium, vinyl lithium, if you treat with DMF, this is the structure of DMF. So lithium is going to attack to the carbon group and it will going to come back and get rid of the NMe2 to get to this product. Okay. So the carbon will get out, there will be a CHO going to introduce and there will be double bond here. So now if you look into all the different options, I can see the option number A is the correct structure, but the B or the C or the D don't have the correct structure. So the A is the correct answer here. So now we are going to talk about what is the major product A and B in the following reaction sequence. So if you look into this particular compound, by looking into the compound, I can see this compound can be called as a 1,3 dicarbonyl compound. If you can 1, 2, 3. So it's a 1,3 dicarbonyl compound. You treat it with 2 equivalent of LDA. So let's try to understand first what is happening here. So I think we have already learned before that if you have a 1,3 dicarbonyl compound, then the proton in between this carbon is the highly acidic one, because it is having two different electron withdrawing group, correct? So if you give a base LDA, it is going to abstract that proton and form the corresponding carbon ion, and you can write that. Now if you treat with one more equivalent of LDA, which is the next acidic proton, this is the acidic proton, the CH3 carbon, correct? CH3 attached with the carbon group. So now if you treat with another LDA, this will go for a deprotonation of this proton to generate another carbon ion here. Okay, you can write it like this also as a enolate form. So now if you have this dienolate form and you treat with allyl bromide, what is going to happen? How it will trap with electrophile? Now if you try to write that down, that you have electrophile here, you can think about this minus will come back and this can able to react. Okay. Because these are in a conjugation, so you will be able to form okay. So this will be your compound A. Okay. Of course, once you have a O minus, you can write lithium plus, and if you look into all the different options, you can see in this option also has the correct structure, and of course here also you see find a correct structure. Both in option A and B, we can see the A is correct. Now what will happen if you treat with lithium aluminum hydride and H3O plus? Again, instead of writing this in the enolate form, we can also write it, you can also, if you get a proton here, because it will not going to stay at the end of the reaction. It once you quench the reaction, it will convert to this compound, correct. Now if you take this compound, treat with lithium aluminum hydride. Again, I talk about lithium aluminum hydride when I talk about hydride reaction in organoboron part. So that this is a very reactive one. It is going to reduce both the the ketone and the ester. In case of ester, it is going to reduce twice, because first if you do reduction of the ester, it will going to generate corresponding aldehyde. It will go for further reduction, because aldehydes will be more reactive than ester. It will go all the way to the corresponding primary alcohol. So you will get, and this ketone is going to reduce to the corresponding secondary alcohol. So you will have a secondary alcohol and a primary alcohol here. Okay. Now if you look into the different answer of A and B, we can see in case of A, this looks the correct answer, but if you go to the option B, this does not looks the correct answer, because the carbonyl will be also reduced here. Okay. So the option A is going to be the correct answer here. The major product formed in the following reaction is, so again there is three different reaction happening. First they are using LDA to abstract a proton, so that should form some sort of enolate. Then they are treating with this ICH2CH2CH2Cl. Again it's a alkyl halide happening, so after enolation there will be alkylation happen, and then you are treating with methyl magnesium bromide and then H3O plus, quenching with the acid. So let's see how this. So if you look into this particular compound, which proton will be acidic proton if you give a base. Of course the this side of carbonyl will have a double bond, so these protons which is next to the carbonyl will be the acidic proton. One of them will be abstracted once you give LDA. So we can understand, if you give LDA, this is going to form this corresponding enolate. Okay, now you treating with ICH2CH2Cl. So of course this is a alkylation going to take place. So if you write CH2I and then CH2CH2CH2Cl, 1 2 3 4, there are 1 2 3, there are only 3. So this is a Cl here, so this is going to come back and go for ASN2 reaction. So it's the enolate alkylation happening first, and now what is happening? So this is going to be your A. So now if you look into all the different options here, we can clearly see in option A, this is cannot be right. The one here also cannot be right, because the iodine will be better leaving group. So this option seems the correct option. Now we have to also consider what will be the option B. Again, once you got A, now if you treat with methyl magnesium bromide, what is going to happen if you treat with methyl magnesium bromide? We know that methyl magnesium bromide is a hard reagent, so it is going to react with your carbonyl compound. That will, and then that will generate this OA, O minus, that will generate this O minus and methyl here, and you have this corresponding Cl here. Okay, and now what you have done, once you take this compound all the way, you have O minus methyl and OAT, you give H3O plus, some dilute HCl. Once you give dilute HCl, there is couple of things going to happen. One is that this will be OH, and then you have a methyl, of course this part will get protonated. So this will get protonated here. Okay. Once you have, I think you can think about that this, this OAT can able to take a proton like this, and it can hydrolyzed. Okay. Okay, I think first thing going to happen, let's leave this first. So once you have this one, we cannot find any any answer. We can see in this answer there is a double bond here. Okay, so let's think if you have this OH and methyl, here we are bringing a double bond, and here you are bringing a carbonyl. That means what is going to happen? This vinyl ether, okay, vinyl ether in presence of a H3O plus, it is going to hydrolyze to the corresponding ketone. So your vinyl ether going to convert to the corresponding carbonyl group here, and now you have a OH and a methyl, okay. So this can get protonated, and these are the protons going to be the acidic. So this can eliminate, it can able to convert to a very similar to the corresponding aldol type reactions, like where you have a carbonyl group and an elimination happen to get to the corresponding condensation product. Okay. So this will be the your the correct product which is going to form. So that will be your B. Okay. Now if you look into the answer, of course this is the going to be the correct answer. So option C is the correct option here. Okay. The major product formed in the following reaction. So here you have this corresponding cyano group where the Grignard is going to get attacked. So you have this phenyl with a where your ethyl magnesium bromide going to attack on the carbon, NMGBr, and you will have a ethyl here. Now, of course, once you have a H3O plus, this can protonate this, and as well as once it can take you to the NH, and then also once you have a H3O plus, this is a imine, this is a imine, this is from iminium and going to hydrolyze to all the way to the corresponding ketone. So this will be the your product. So you can see this is not the correct option, this is the this is going to be the correct option here, option B. Okay. So if you treat with the aryl cyanide in Grignard, you will end up getting to the corresponding ketone. So you can see option B is the correct option. Again, in this particular part, I talk about some of the problem from organolithium and also from the carbanion. Also I will encourage you to practice more problem, and if you have any other queries, of course you can come back in the chat. Okay. So thank you so much for coming to the class, and I'm going to see you in the next class. Thank you.